Everyone, it is a challenge to be the first lecturer after lunch. I hope I will succeed in keeping you awake in the next 20-30 minutes. So I'll begin my story about quantum mechanical, the quantum confinement effects in self-assembled peptide nanostructures and proteins. And we will start with biology. The story starts with biology, with peptide amyloid fibrils. We know today there is more or less 20 amyloid diseases, and one of the most feature characteristics of them is the creation of amyloid fibrils. Here on the left of the slide, we can see an example of amyloid fibril, which is the cause, in this case, for the Alzheimer's disease, which is self-assembled from a small protein called the A-beta protein. This fibril, as you can see, is made by stacking of layers in a beta sheet formation. And on the cartoon on the right side of the slide, we can see how the self-assembly is occurring from a soluble monomer to an insoluble fibril. So in 2003, Udi found that one of the most common features of the amyloid proteins is the existence of aromatic amino acids in the middle of the amino acid sequence of the protein. As we can see here, this is the amino acid sequence of the A-beta protein of the Alzheimer's disease. And in the middle, highlight two letters, FF, which stands for 2 phenylalanine residues. And we found that if we take in only this small element, which composed only from 2 amino acids, we can get peptide nanotubes. Those peptide nanotubes are highly rigid. So from 2003 up to now, many groups in the world are working on the same peptide nanotubes we compose from small aromatic amino acids, along with Udi's group, where I started my PhD. So we can take several kinds of small dipeptides, whether it's the FF peptide nanotubes, which you can see here on the right. We've got a new techniques in Gil Rosenman laboratory to take this small FF molecule and by evaporative deposition techniques to create surfaces. You can see same image of the surfaces on the left side of the slide. We can take the same FF and in fast evaporation from organic solution we can make a nanoforest. We can make also on the left side of the slide spaghetti-like fibrils from an analog of the FF molecules, which forms a hydrogel in aqueous solution. It contains the water and creates nanopools in the order of dozens of angstroms, and that's a hydrogel is formed, a very rigid hydrogel. And also I will talk about spheres and nanodots. We can make, depends on the environment, we can make from the same FF molecules or an analog of the FF molecule nanospheres or nanodots, which I will mention later. So, how my story begins. I started in biology. I've done some experiments and focused on the optical properties of the if it's a single peptide nanotubes or a surface of peptide nanotubes. And this was one of my first measurements, which started all this process. We can see here a simple optical absorption spectrum. The red curve is the FF monomer. We can see the peak, which located in 257 nanometers. However, when we took the surface of the FF peptide nanotubes, we receive a completely different optical absorption. You can see here on the black curve, which adopt a step-like optical absorption. And we thought, what is it? Because it's interesting. Suddenly start to absorb light not only on the UV, also in the visible. And this began all the process of what I call quantum confinement. So step-like optical absorption spectrum is immediately led us to the term quantum confinement, and I will spend 1 minute just a little bit to explain what is quantum confinement. Usually when we're talking about solids, bulk materials on the left of the slide, the electron can move in 3D in all of the directions. On the bottom side, on the bottom of the slide, we can see the density of states, meaning in general the statistics of the electron to be in a certain energy. And we can see a continuous curve. The electron can move on that curve, and if we split it to quasi-states, we can see the difference between each energy level is on the order of 10 to the minus 15 electron volt, which is very low. However, when we start to confine the bulk materials, we can do it in several levels of confinement. The first level is a 2D quantum well. The electron can move in 2D direction. I have only 1D level of confinement. And as you can see, the density of states changes to a step-like density of states. Here, the difference between each step jump to the order of 1 electron volt, much higher than each energy level of the bulk material. I can further confine it into quantum wire. The electron can move only in one direction, and a common quantum confinement structure called the quantum dot, where the electron cannot move. It confines in the same small area. It creates an exciton, which is a pair of electron in hole. And the energy here between the levels can reach up to 3 to 4 electron volt, which also gives special photoluminescence properties to quantum dots. One of the pioneers of quantum confinement was Canham in 1990, which creates mesoporous silicon islands, and he creates photoluminescence from silicon, silicon is an indirect semiconductor, so it shouldn't create photoluminescence. So over the years, many of structures have been studied and found special electronic characteristics which are due to the special density of states, and one of them are photoluminescence. So I continued to study the photoluminescence of the peptide nanotubes. Here on the dashed line on the curve, we can see the photoluminescence of the monomer. The monomer, the main photoluminescence of the monomer is from the phenylalanine ring. It's a chromophore, it's absorbed light, it emits light, and it emits at around 290 nanometers. However, when we studied the photoluminescence of the peptide nanotube surface, we observed that the first UV peak is also shifted in about 15-20 nanometers, and we receive also a small peak at around 400 to 500 nanometer, which was very noisy. So we thought, what is the origin of this peak? Because simple phenylalanine will never create photoluminescence in these wavelengths. So we've done some PLE, photoluminescence excitation, and we found that the main source for the luminescence in around 450 nanometers, which is blue, is actually located at 370 nanometers. If we can also see the absorption spectrum on the left, it falls exactly on the second step of the quantum well, where the first 305 nanometers peak is located on the first step at the quantum well structure. We can see also that the photoluminescence intensity is much higher than the photoluminescence at the UV. So we receive a really blue luminescence from the peptide nanotubes. So immediately we design a little bit of patterning system to see the blue luminescence in microscopy, and I will show you two examples. The first example is we know how to pattern the surfaces of peptide nanotubes. So I just pattern squares of peptide nanotubes. You can see here the same of each step. I excite the molecules at around 370, and you can see the blue emission coming out of the peptide nanotubes. Another example is single peptide nanotubes. You can see here the same image of the peptide nanotubes, also exciting the same wavelengths of the deposition, and you can see the strong luminescence coming out of the peptide nanotubes, which is basically composed only from phenylalanine, which is completely not visible in these kind of ranges. So we want to further study the whole mechanism of the creation of the quantum confined state and also the formation of the exciton. For that I went to hydrogel, also the spaghetti-like peptide nanotubes, which I showed at the beginning of my lecture. And in the hydrogel system, I can play with the concentration. At low concentration, I don't receive any hydrogel at all, and as I increase the concentration, I receive the peptide nanotubes and I receive the hydrogel formation. So let's look first on the upper graph. We can see at the black curve, the lowest concentration. We can see the main peak of the monomer, which is located at around 260 nanometer. This is the intrinsic absorption peak of the monomer. And if we can go a little bit to the right to where the wavelength, we can see a small peak over here at Chupchik, which is unique. And it's located at the red edge of the peak. This peak highly resembles to the absorption peak of quantum dots, which is a peak-like absorption spectrum. And we can see that as we increase the concentration, and in a certain concentration above 0.4 milligram per ml, I receive the peptide nanotube formation and the hydrogel formation, and we can see that the monomer peak is completely disappearing, and we receive from the small peak a step-like absorption spectrum. So we can really follow the dynamics of the creation of the structures from a small nucleus, which looks like quantum dot, into a full structure which looks like quantum well. At the bottom curve, it's my negative control. It's exactly the same molecules, only in a condition where I cannot form any nanotubes. And we can see that even going to high concentration, twice more than the highest concentration of the first graph, I don't receive any step-like absorption spectrum, and it's mainly the absorption spectrum of the monomer. Another unique characteristic that we found is by following the photoluminescence excitation of the structures. The photoluminescence excitation is basically like the absorption spectrum, but I detect the photoluminescence at a certain point and just excite the molecules at different wavelengths. So if we start from the negative control, we can see no matter the concentration, the photoluminescence excitation is broad, which is quite usual to organic molecules, and only not organic molecules, the photoluminescence excitation is usually broad. However, if we look on the graph of the hydrogel, of the peptide nanotubes formation, we can see the transformation from a broad photoluminescence excitation on the black curve into a very narrow optical photoluminescence excitation after the gel is formed. This full width at the half maximum of this PLE peak is only 4 nanometers and even less than that. So it can tell me that an exciton is formed and also a nanocrystalline is formed, because if wasn't, I would receive exactly like the bottom curve, a broad photoluminescence excitation. It's almost a discrete excitation level. Here I follow the dynamic of the process by the photoluminescence excitation, and we really can see the formation of the narrow peak. Here on the graph I can follow also the intensity of the peak, which increase after the gel is formed approximately after 2 minutes. And then it stabilizes, and we can see the FWHM, full width at half maximum, also until we receive a very narrow level of actually 3.75 nanometer, which is very low. After that, I wanted to see if I can receive the quantum dot formation that I get at the beginning of the process. For that, I took the usual peptide nanotubes and just dissolved it in methanol. After I dissolved it in methanol, I went to spectroscopic. I will show it in the next slide. And I received exactly the same. I can see the exciton, you can see the discrete excitation level. So I thought to myself, what is going on here? So first of all, I took it to the AFM and to see what I have in this clear solution. The solution in the beginning was the peptide nanotubes aggregate. So you can see kind of white solution, and after the dissolve process, the solution gets clear, And I noticed lots of spots, lots of dots on the surface of the mica. Here on the left bottom graph, you can see a cross-section of the dots, and there were exactly 2 nanometers in diameter. I've done some analysis, and I received by statistics that the dots have a diameter of 2.1 nanometers, which is very low for conventional quantum dots, which we can make in flux or anything. So here are the results of the spectroscopic of the same dots that I received, and I got that the optical absorption of the dots were exactly like the optical absorption of the peptide nanotubes. It's a spike-like optical absorption, which resemble the optical absorption of quantum dots. And also the PLE, we can see from a very broad optical PLE spectrum, I received again the very narrow PLE spectrum where the dots are formed, or where I dissolve the peptide nanotubes. I get exactly the same spectrum. So I took it further analysis. I took it to XRD, and I received exactly the same XRD patterns to the peptide nanotubes and found the peptide quantum dots, I call them. It's a P61 hexagonal space group. Also, I took it to TOF SIMs and mass specs, and at the TOF SIMs, I noticed that the molecular weight of these dots is 623. And 623 is exactly 2 D-phenylalanine molecules. So I guess the dots are made from 2 phenylalanine, which form together due to aromatic interaction, because we have only aromatic amino acids over there. And they are very stable at solution, as we could see at the AFM. Also, the mass spec told me almost the same, that it's composed from 2 D-phenylalanine molecules. So we thought to ourselves, we have a crystalline structures. I have a nanocrystalline region. I used some quantum mechanical equations. I didn't want to put them. It's way too much for this time of the day. And all the nanocrystalline regions are of the order between 10 to 13, 14 angstrom, only slightly above 1 nanometer, which is very small. And we have P61 non-centrosymmetric space group. So we thought to ourselves, we've got kind of ceramic-like structures which compose from thousands of small crystalline regions in the order of the nanoscale. What can we do with it? So the non-centrosymmetric space groups and the highly crystalline structures immediately led us to 2 fields. One of them is nonlinear optics, and the other one is the dielectric field, which this P61 non-centrosymmetric space group should have piezoelectrics, should have pyroelectricity, and should have ferroelectricity. We started on piezoelectricity. So this is the basic of piezoelectricity. I don't think that I need to explain much, but it's when I applied high voltage, I can create strain at the crystal, and vice versa. When I create strain at the crystal, I can create voltage. So one of the best ways to measure piezoelectricity in the nanoscale today is piezo force microscopy, which is based on regular AFM. So this is on the right side of the slide, our technique, how we measure piezoelectricity with PFM. We apply voltage to the tip, and in contact mode, by applying the voltage, I create also the electric field. I can follow the piezoelectricity of the sample. I can follow 2 ways of motions. I can measure the out of plane, meaning when I apply in the field, I measure the strain in the same direction of the field, which is out of plane, and I can measure the in-plane motion of the crystal when I apply in the voltage, and I measure the strain in a perpendicular way to the electric field, and then the tip is going a torsion move, and I can follow it on the photodiode of the AFM. And here we can see our results with the peptide nanotubes. On the left, we can see, on the up, we can see the in-plane, and here the down, we can see the out-of-plane signal. As we can see immediately, we've got only in-plane signal and not out-of-plane signal. Why is that? Because apparently the polarization vector, the spontaneous polarization vector of the peptide nanotubes is along the peptide nanotubes and not perpendicular to the peptide nanotubes, which kind of makes sense in a way. We can see bright and dark tube on the upper image, and why is that? It's kind of arbitrary. If we've got one tube with a polarization vector up and the other one standing next to him with the polarization vector down, so I will receive in the AFM one dark and one is bright. The best way to check it, if it's really true, is just physically rotate the sample in several degrees. So if I've got one up and one down, when I rotate it, it will be the opposite. So here we can see the results. We can see here the difference between, for instance, 0 degree and 180 degree. And we can see all the bright tubes become dark and all dark tubes become bright. And it's really strengthens our theory that the spontaneous polarization vector is along the peptide nanotubes. On the left side, we can see a common detection for study if it's really piezo and not just electrostraining effects. And we can see here increase on the voltage of the tip, and we can see a linear response on the in-plane polarization vector. And we can see a straight line, which is a characteristics of piezoelectric crystals. We also done some experiments with comparison to common piezoelectric crystals, like lithium niobate in this case. And we can see more or less it's in the same order. In this case, the peptide nanotubes got piezoelectric signals about a half of lithium niobate in the in-plane directions, but lithium niobate is one of the highest polarization vectors in plane directions that there is. Okay. The second field that I mentioned is nonlinear optics, which derives from the non-central symmetric crystals. I will not get further details what is second harmonic generation. We heard before the very nice talk of Adriari. Explained it, it's very nice. Here we've measured the second harmonic generation. For start, on the left side, we can see the intensity that we receive after increasing the input power of the laser. We use the titanium sapphire laser here. On the middle, it's the same graph, only in log-log scale. We can see that at low input power, we can receive a second harmonic generation behavior. It's got an increase of 2, which is very common for second harmonic generation crystal. But we noticed some interesting phenomena that at certain input power, we've got a sort of threshold, and we receive a really sharp increase of the photoluminescence that we detect from 2 in the second harmonic generation state to around increased 8-fold, which was rather unique. Why do I get it? And so on the right side, we can see the spectrum for one of the reasons that we receive this high super photoluminescence, we call it at the beginning. And we can see the normal spectrum that in low, we can see the sharp peak of the second harmonic generation, which is a multiply of the input power laser. And we can see that at around 400 nanometers, we get an increase in the photoluminescence. The increase is reaching up to around 800 nanometers, up to the red side of the spectrum. And the result of this increase was actually getting a white light from the peptide nanotubes. We can see it here on our photos. This is our experimental. On the left side, we can see when we put the laser on the gold surface, we don't receive any second harmonic generation. However, when we move the laser point to the peptide nanotubes, we receive the strong second harmonic generation signal. We can see now the peptide nanotubes are blue, and the laser is red. And we can see quite clearly the white light going out of the peptide nanotubes. The second harmonic generation that we receive, it's not the usual second harmonic generation which occur in regular crystals. It's an excitonic-like second harmonic generation. We can receive it only when we excite inserted wavelengths. By the way, the excitonic location is it's matching the excitons that we found when I started to talk. It's just you need to divide the values in two, and then we receive the exactly same location of the excitons that we received in our previous studies. And also this unique super photoluminescence is also origin for an excitonic-like, meaning that you can excite it only at certain points. This is the model of the peptide nanotubes and a little bit what we think that occurs over there. We've got the peptide nanotubes. It's got an hexagonal symmetry. It also looks like an hexagonal. And it's got multiple hollows in the order of 1 nanometers inside it, which go along all the peptide nanotubes. I believe that the nanotubes is created from nanocrystalline regions in the order of 1.2, 1.3 nanometer, which compose from 2 phenylalanine residues, where we can see here on the blue square over there. And each crystal can give in the second harmonic generation, as we can see here on the wavelengths. Another phenomenon, the white light, is probably can relate to a known phenomenon in nonlinear optics called supercontinuum. And when I started to read about supercontinuum, I found that the most studied crystal in supercontinuum was photonic crystals. And for my surprise, the first figure in my review that I read was a picture of photonic crystals. Photonic crystals is a fiber with multiple channels on it, and the optimal space group of the optical fiber is an hexagonal. So we've got almost here an optical photonic crystals, only in nanoscale. This, I think, brings the white light. And I will finish my talk. We'll return to biology. And from our new understanding that a nanocrystalline region is formed only by using small deep peptides, I went back to the amyloid proteins, and I find a unique spectroscopic also in amyloid proteins. I started to study the insulin because it's cheap, basically. But it forms amyloid fibrils, as we can see here in the AFM. It's crystalline. We can see here the diffraction. And I can see also the creation of a step-like behavior after the creation of the fibrils, and also the creation of almost the same exciton as I can see in the FF. I can see also in the insulin case. When I started on pre-fibrillar state, I can see the creation of crystals. And I just look at a little bit crystal structures of insulin, and indeed insulin created at the beginning dimers, and I highlighted the phenylalanine of the insulin, and it creates almost the same crystal structures that only FF creates in a solution, and also in its further self-assembly creates an hexamer, and we can notice again the same FF nanocrystalline structures that I can get only by using FF here. They are creating on the protein itself, which gives the unique quantum mechanical effects. And that's it. I need, first of all, to acknowledge my two supervisors. And as Ori said at the beginning, one is Tzfoni, Udi Gazit from biology, and one is Dromi, Professor Gil Rosenman from engineering, who let me do all this stuff. And our collaborators, Michel Molotsky for the theoretical calculation, quantum mechanical calculation, Danny Hooper, which it's always fun to work with, and our two collaborators from abroad, Andrei Kolkin from Portugal and Lena Mishina from Russia. And thank you for listening.